Right, I'm thinking about becoming a stand-up comedian. I've decided that lecturing doesn't pay the bills anymore, so I'm going to become a stand-up comedian. Okay? There are 10 types of people in this world. Those who understand binary and those who don't. A tough crowd. It's a bad joke. Do you get it? Yeah. Okay. How many people can count in binary, add in binary, work in binary? Who doesn't know what binary is? You want to know what binary is? Try to skip a large bit of this lecture. Okay. Well, we'll look at binary. We count normally in base 10. Why do we count in base 10? Okay, fingers and toes, unless you come from my neck of the woods where some people have 6 fingers. I thought I'd get that joke in before everyone sort of says it. Okay, I'll start with the jokes. I'm no good at it, I do know stuff. Okay, consider the number 1234 in base 10. Okay, dead easy for you, you know what it is. Back in primary school, you learned that you had units, tens, hundreds, and thousands. And that's how we have a value. That's how we express numbers in base 10. We have 10 symbols to express our numbers. Okay, this comes from the Arabic symbols. Back in the day, back in the Roman times, they used I, B, X, L, C, etc. Very, very poor for mathematics. The Arabic mathematics at the time, the Persian mathematicians were using these symbols like this. And that was a huge step forward in mathematics. Okay, so in the 4-digit number 1234, we know that the 4 means 4 units, the 3 means 3 tens, 2 means 2 hundreds, 1 means 1,000. Well, what you have is in base 10, the unit is 10 to the power 0, the tens is 10 to the power 1, hundreds 10 squared, 1,000 and cubed. So you can see the pattern. Starting at the right-hand side, you've got 10, you've got the base, which is 10 to the power 0, and then you just add 1 to that power as we go a digit to the left. That's base 10. That's what you've been counting in. What about binary? Now, binary is base 2. So we only have 2 digits we need. Okay, we only have 2 symbols. We use 0 and 1. And the position of the digit carries the value much the same way as it does in base 10. For example, the binary number 111, it means if you start on the right, 1 times 2, which is the base, to the power 0. 1 times 2 to the power 1. 1 times 2 to the power 2. So if I wanted to represent, if I want to calculate what 111 is in binary as a decimal, the decimal number, I have 1 times 4 plus 1 times 2 plus 1 times 1, which is 7. So 7 in decimal is 111 in binary. In other words, the value of each digit to the left is double that of the value of the digit to the right. Why am I teaching you this? Well, the next clipping algorithm uses binary numbers. Okay. And this method is called the Cohen-Sutherland clipping method. It only works when we have a rectangular clipping region. So can you think of an application where you have a rectangular clipping region on a computer? What about a window? Windows on computers are rectangular. Okay, so when anybody know who invented the Windows system, graphical user interface? Sorry? Nope. He nicked it from Apple. Oh. But Apple nicked it from somebody else. Okay. Xerox. Ever heard of Xerox? Yep. They invented this graphical user interface. Apple liked it, and they said, "Could we have it?" And Xerox go, "Yeah, right." Without paying us a penny for it, they gave away a massive asset. So Apple then had the Windows system, Bill Gates was invited to Apple, and Apple was showing off to Bill Gates what they did, and Bill Gates nicked it. So, and the rest is history. But anyway, so Cohen-Sutherland method is very useful for windowed systems. And what we have is, if you think about a window, we have 9 regions, or 9 possible areas where a point can be relative to that window. If we have this sort of dark area as our window, if our point is within the window, we give it a binary number 0, 0, 0, 0. If our point is anywhere in the 8 regions around the window, we give it these binary numbers, and these are called bit codes. That may look a bit random, okay, but there is method to these bit codes. Okay, and the method is, the first digit is a 1 if our point is above the clip region. So look at all the ones on the top. That, for each of these numbers, the first digit is a 1. All of these down here, the first digit is 0. Okay, because it's a point being anywhere around here is not above the clip region. The second digit is whether it's below the clip region. So if you look at these 3 points here, okay, we see a 1 in the second location. The third digit is a 1 if our point is to the right of the clip region. So if you see here, each of these has a 1 in the third bit location. And the last one, the fourth bit location, is if it's to the left. Okay, so you can see each of these has a 1. Okay, so you go top, bottom, right, left. So that's the, so it's not random the way these numbers or these bit codes are assigned. It's all to do with what, where is that point or where is that region relative to our clip window. And you'll notice within our window, it's 0, 0, 0, 0. Okay, so first thing to do is bear that in mind. We assign our endpoints of our line a bit code each. Okay. And with these bit codes, we do 2 operations. One is bitwise and one is bitwise or. 2 bit codes are equal if all of their digits are equal, like any other number. Okay, so don't really have to say much about that. Bitwise AND is similar to the logical AND. Okay, and what we do is we do a logical AND on each corresponding digit. So, for example, here, the first digit is a 1, and the second digit is a 1. That's true. We have a 1. Here, the first digit is a 0, but the second digit is a 1, so they're not the same. 0. First digit is a 1, second digit is a 0, so they're not the same. First digit is a 0, but second digit is a 0, but they're the same, but neither of them are true. Okay, so this is going back to your logic. Did you do, I think you did logic last year. Truth tables, do you remember all that? Yeah, okay. So essentially, AND is true only if both of them are true. So both of them have to be a 1 for it to be a 1 here. Bitwise OR is, it's true if one or the other is true. So here, we've got 1 and 1, so it's 1. Here we've got 0 and 1. But because one of them is a 1, it's true. Here we've got a 1 and a 0, because one of them is a 1, it's a 1. And 2 zeros give a 0. So bitwise operation is essentially logic applied to each digit, corresponding pairs of digits in turn. Okay, now this looks really, really scary. Don't worry, we're going to go through an example. This is the algorithm of Cohen-Sutherland. What we do is we require a line joining 2 points A to B. And we need a window which is defined by the bottom left and top right coordinates. So x min, y min is coordinate to the bottom left. X max, y max is coordinate to the top right. And we calculate the bit code of A and B, depending on where they are in relation to our click window. This is quite complicated. I'm going to step through it slowly. While the bitwise OR of A and B is not equal to 0. If it's equal to 0, excellent, because it means we can just plot our line. If the bit code of A, bitwise and operation with the bit code is B, is non-zero, that means we don't draw the line. Okay, we reject it. So it means it doesn't enter our clip region. Else, if bit code of A is non-zero, we clip A to whatever edge we clip it to. If the bit code of B is non-zero, we clip B. And we do the same again. We recalculate our new bit codes and go around again. So this algorithm doesn't calculate the coordinates of our clipped point. It only tells us whether they need clipping or not. We shove it into the Cyrus spec and then say, okay, this needs clipping, use Cyrus spec to then clip it. And I'm going to step through a worked example now. Okay, so here we have our same example for the notes. This is our clip region, and these are our lines. We looked at this in the first lecture. Okay, let's have a look at A to B. Both A and B are within our window. So the bit code of A is all zeros, bit code of B is all the zeros. The first thing we check was whether the bit code of A or B is equal to zeros. If it is, happy days, we just draw it. We don't need to do any clipping. Let's have a look at C to D. Okay, now C is within our rectangle, but D is above. So we've got a 1 in the first bit location. So if we do bit code C or bit code D, we get 1, 0, 0, 0. That's not equal to 0, so we have to do something. If it was equal to 0, we wouldn't have to clip, but we do. So this one says, do we have to do anything to our line? The second one, C and D, says, can we reject the line? Okay, so C and bit code D is equal to zeros. Because it's equal to zeros, it means we have to do something with it. If there was a 1 in any of these locations, we can reject it. But in this case, we have to clip. How do we know which one to clip? Well, we have a 1 there, so that says, okay, D needs to be clipped to the top edge. There's a 1 there. So we throw that into Cyrus spec clips it, and then our bit code of our new clipped point D is equal to all the zeros. And we step through the algorithm again. We look at C or bit code D dash, which is the clip point. That is then equal to all the zeros. So then we could draw line C to the clip point D. It sounds a bit clunky. This is an incredibly efficient algorithm. It's efficient because it uses bitwise operations, which is essentially what computers think in. Right, E to F. Okay, we can see using our eyes, but that line E to F never enters our clip rectangle. Okay, so bit code of E, that's to the left, so therefore we've got a 1 in the 4th location. Bit code of F, well that's above and to the left, so we've got a 1 in the 1st location and a 1 in the 4th. Okay, check whether we can draw the line, so E or F. Because this is non-zero, we can't draw the line as it stands. Check whether we can reject the line, E and F. Because this is non-zero, that means we can just reject it. We don't even have to clip it. It's like never enters our window. Okay, so we can just reject that. G to H is a bit of a complicated one. Okay, you'd notice that G is outside, and so is H, but at some point it does cross over our window. So again, same process, calculate the bit codes of G and H. Because G or H is non-zero, we have to clip. But G and H is 0, so therefore we can't reject it. So G is clipped to the bottom edge because there's a 1 in the second bit location, and H is clipped to the right edge because there's a 1 in the third bit location. So the new clip points have 0 bit codes. We do the G or H again, it's 0. So then we draw G, clip G to clip H. Okay, last one. I through to J. Now, by visual inspection, I to J never enters our clip region. But let's have a look at what the algorithm says. Okay, calculate the bit codes. I or J is non-zero, so we can't draw it. I and J is zeros, so we have to clip. Okay. I is clipped to the bottom edge because there's a 1 in the second bit location. J is clipped to the right edge. So what's happening here is I gets clipped to the bottom edge, to that point there. J gets clipped to the right edge, which is that point there. And we start again. What's happening here is all we've done is just swapped over the bit codes. So if I go through the same process again, I don't know whether I've got another slide. Yep. If I go through the same process, it's just going to keep sort of oscillating, keep flipping backwards and forwards. So this is the only time when the Cohen-Sutherland algorithm starts to suffer a bit. So we are now back to the original bit codes. We do it again, and the algorithm will just keep going forever. So if that's the case, we just have a little switch in there that says if you keep doing the same thing, just exit and ignore the line. It's a little bit tricky, the Cohen-Sutherland one. It's not as straightforward as Cyrus Beck. Okay, but why use it then? It's more tricky. Essentially, it's very, very quick. It uses binary operations, which is what computers think in. So it's very quick for them to evaluate. It can determine whether lines are accepted or rejected without needing to calculate anything. So we're not calculating any floating point numbers. By floating point numbers, I mean decimals, anything which is not an integer. It's used in GUIs, which is another word for graphical user interfaces or Windows systems. Disadvantages, it only works with regions which are sized parallel to the X and Y axis. You can have a 3D version of this as well. But that's the disadvantage. So it's not a general method, it's only a method which we use when we've got rectangles. Okay. That's for the next lecture. Right, so if you have a look at page 3 in this, so I'm just going to bypass page 2 for now.